In this next question, we're told the following. A piece of wire 10 metres long is broken into two parts, which are bent into the shape of a rectangle and a square with dimensions x times y and x times x, respectively. Find the dimensions x and y that make the total area a maximum. So in this particular problem, it's a little hard to get our head around it, so let's just draw out what we're doing. So it shouldn't be a squiggly line. Got a piece of wire. We're going to cut it into two pieces, and from those two pieces we are going to create a rectangle out of one piece, and we're going to make a square out of the other piece, and we're told that this rectangle is x by y and this square is x by x. So the key thing here, of course, is that the height of the rectangle is the same as the side length. Okay, and we're told that we can cut this thing anywhere, so obviously when we cut this, it's going to change the various dimensions of these shapes, and we want to make the total area. So if we call this one A1 and this one A2, we want to make that thing a maximum. So the thing that we're maximizing here is area. So we are, of course, after a function a of x, and we are going to have to again knock out the y from this. So let's have a look at this. My two areas are a1 and a2, so my area function is going to be a1 plus a2. a1 is going to be x times y, and a2 is going to be x times x, or x squared. So this will be my area function. The only thing left to do is to replace the y with some sort of expression involving x. So to do that, to get that expression for y, we're going to have to use some of the other information in the question, and the information is going to be here. Okay, we know that the y is 10 metres long, so the total of these two perimeters has to be 10 metres. So if we look at those shapes, and we put in the other lengths, we've got 6 x's, 1, 2, 3, 4, 5, 6, and 2 y's. I just rubbed it out by accident. But what we can work out is that, well, if I have 6 lots of x and 2 lots of y, those must total to give me 10 metres. Okay, the total of these perimeters has to be 10. And rearranging, I can get an expression for y. So I get that y is equal to 5 minus 3x there. And we can replace that in here. And now I've done all the hard work with this problem, and that is getting an expression. And from this point forward, it's going to be a matter of just solving this equation to work out where it's going to be maximal. So let's do that. Here's my expression. It's going to come out as a quadratic, which is nice. We can deal with quadratics. Squared, I don't mind blank there. Okay, again, this is nice. We can tell that this function is going to have a maximum because we have a quadratic function, a parabola, and we've got a negative coefficient on that. So it's going to, again, be a concave down parabola with this kind of turning point up here. Okay, so differentiating that, I get a dashed of x is 5 minus 4x. Stationary points, they are going to occur when when a dash of x, the first derivative, is equal to 0. So in this particular case, I'm going to get 5 minus 4x equals 0, or x equals 5 on 4. So that is going to be the optimal length. That's 1 1/4, 1.25. So 1.25 is going to be the optimal size of x. If I want to work out what y is going to be, I'm going to have to use this equation here. So y is going to be 5 minus 3 times 1.25, which is going to be 5 minus 3 3/4, or 3.75, and that's going to be 1 1/4, 1.25. Okay, so that means, isn't that interesting? The two optimal shapes are going to be two squares. Okay, so these things here, the rectangle, okay, are going to be, is going to be 1.25 by 1.25, and the square is also going to be 1.25. That's the worst square I've ever drawn, but that's okay, 1.25. So that will be the optimal dimensions if you actually make both of these things square in shape, equal lengths on the sides. That will be the maximum area that we can get.